All right. Welcome, everyone. We're going to wait a minute for folks to join, and then we'll get started. I see people trickling in. Welcome, welcome. Get started in just a moment. Hello, hello.
Hi,
All right.
Moreno.
We're about 1 minute in, so we'll go ahead and kick things off. But hi, everyone. Welcome to today's webinar on detecting and preventing account takeover at scale and with real-time fraud signals. I'm Julia Bruyette. I'm a product marketer at Tecton, and I'm joined by Sergio, our developer advocate, who will be walking you through a really cool live demo shortly. Sergio, do you want to introduce yourself real quick?
Well, you kind of just did, but yes, hi, Sergio Farragut, developer advocate. Been at Tecton for about a year now. My background is in data warehousing, ETL, all sorts of data analytics. But I'll let Julia kick us off.
Sounds great. I'm going to share my screen here. There we go. Okay. Before we dive in, just some quick housekeeping things. We'll save some time at the end for Q&A, so please drop your questions in the Q&A tab, which is right next to the chat window on the right side of your screen. This session is being recorded, and we'll share the recording along with additional resources afterward. We're also going to run 3 quick polls throughout the webinar to better understand your fraud detection needs and challenges. And your answers here will just help us tailor the follow-ups that we send to you with what's most relevant to you. So I encourage you to respond to those when you see them pop up, and I'll guide you to where to respond when the time comes. So let's take a look at what we'll cover today. First, we'll talk about the account takeover threat landscape and why it's such a critical problem to stay ahead of. Then we'll dive into some core technical requirements for effective ATO prevention. Sergio will then walk us through his live demo showing you how you can build real-time ATO signals. And then finally, we'll wrap up with a brief case study. So let's jump in. We'll start, with talking about the scale of account takeover fraud. The numbers here are pretty staggering. As you can see, this is all sourced from Javelin's research, but it's about a $16 billion problem. Causes $16 billion in losses just in 2024 alone, with nearly 1 in 4 consumers reporting being victims of ATO. But what's particularly alarming here is that 42% of those ATO victims had a bank account compromised. So while ATO is not confined to just financial institutions or fintech companies, it can happen anywhere where like a user account is involved. But in the fintech space, the stakes are particularly high. And while the financial losses are significant, many of our fintech and financial services customers tell us that the reputational damage can actually be even more costly. If people have their accounts compromised, it can easily create a PR mess that erodes trust in your platform. And in fact, one fintech team that we talked to shared with us recently that their ATO model is the most scrutinized model in the entire company. So this explains why machine learning teams pay a lot of attention to this and improving their ATO detection systems. And we'll talk about some of the technical challenges that ATO presents. But first, I'm going to kick it off with our first poll. This is a new thing for us, so be patient with me. But I'd like to get a sense of where everyone is at with their ATO fraud detection journey. So I'm going to launch the first poll now, and you can respond to it you'll see the poll tab pop up in the right-hand side next to the chat. So you'll see the question there is, where are you at in your fraud detection journey? Awesome, I see some responses coming in. Thank you for responding there. I'll give it a couple more seconds, and then we'll go back. Nice, okay. I'm seeing a lot of folks are just starting to explore fraud detection in their org. A lot of people also using ML models, but not in real time yet. And then quite a few of you are also running real-time ML in production. So that's awesome. I'm going to go ahead and close this and reshare. Okay. So thank you all for responding. I think what makes ATO particularly hard to detect is the rapid evolution of attack methodologies. So what we're seeing is a clear progression in sophistication, right? From the early 2010s when attacks were primarily basic credential stuffing, exploiting people having reusing the same passwords across multiple sites. It's, pretty straightforward stuff. But by the mid to late 2010s, we're seeing things become a bit more sophisticated. Attackers are using advanced methods to do identity manipulation. They developed techniques to bypass the IP-based defenses that were put in place, for basic fraud detection by spoofing actual legit devices. And then in the early 2020s, we saw the rise of authentication process exploitation. So specifically targeting the vulnerabilities in multi-factor authentication systems through, techniques like SIM swapping and social engineering. And then now we're in the era of AI-driven behavioral mimicry, which can actually defeat behavioral biometrics and anomaly detection. So these systems are really advanced. They can simulate legitimate user behavior with pretty scary accuracy. And each of these evolutions create new technical challenges for security teams and require even more sophisticated detection systems to catch. It's basically a constant arms race that's been driving the shift from classic rules systems to and rules engines to more and more advanced machine learning in this area for the past couple of years. So let's talk about the challenges here, or the second challenge, which is the real-time nature of ATO fraud. So for account takeover detection, fresh data is critical because sophisticated attacks happen in real time and evolve really quickly. So ML systems typically need a few types of data to make the best decisions. First of which is historical data. You see here includes things like login history, transaction patterns, risk scores, essentially establishing a baseline behavior for each user. What's normal for them? When do they typically log in? What devices do they usually use? That kind of thing. The second is streaming data. So recent login attempts could be, device fingerprinting, IP address changes, things like that, which show current trends and potential anomalies developing in real time. But the third type of data is real-time data. So that's what's happening right now. The current geolocation, behavioral biometrics like typing patterns or mouse movements, input speed, These things capture like the immediate context of a login or an account authentication attempt. So, at the point of login or trying to authenticate a user, what is the current state of reality? And without the streaming or real-time data, you're essentially trying to fight right now's fraud with yesterday's information. So the key technical challenge here is that these different types of data typically live in separate infrastructure. Your historical data is probably in a data warehouse. Your streaming data is likely in Kafka or Kinesis, and your real-time signals might be coming from direct API calls or application servers. So bringing all of these types of data together consistently and serving it to models at millisecond latency is a pretty big engineering challenge. So moving on to the third challenge, which is scale. So for a large enterprise, this means processing potentially hundreds of thousands of queries per second. But for pretty much any B2C platform, you need to maintain sub-second SLAs consistently while managing the auto-scaling infrastructure to handle traffic spikes. But you also want to keep costs manageable, so there's a lot to balance there. And we're calling out just a few of the data engineering challenges that come with this. You need to transform data, raw data into useful fraud signals, so features for your models. You need to manage backfills when you recalculate historical features, ensuring you have consistency across your entire data set. You need to meet those strict SLAs. You also need to ensure connectors to various data sources and your different systems. You need to ensure data consistency between training and serving environments. And you need to scale your storage and compute efficiently to balance that cost performance trade-off. So most companies end up with, what we think of as like bespoke infrastructure, very custom, built by very talented engineers, but requires pretty much constant maintenance and specialized knowledge. It's kind of like building a Formula One car in your garage. It's super impressive, but not something that most organizations can or want to maintain over time. So now that we've talked about some of the technical challenges, I'm going to do our second poll now because I'm curious about what you're finding most difficult in your fraud detection efforts. So let me go ahead and launch that next poll now. Okay, you should go ahead. You should see that poll is open now. You can access it on the right side of your screen next to the chat window. The question is, what's your biggest challenge with fraud detection today? Is it data pipeline complexity, slow signal development, or iteration? There's lack of labeled data. Is it model performance and accuracy, real-time inference at scale, or cross-functional alignment between your engineering and data science teams? Or if it's none of the above or something else, please feel free to share in the chat. We'd love to know. I see a lot of votes coming in. Okay, I see a lot of cross-functional alignment is a challenge, as well as real-time inference. Good to know. This aligns really well with the requirements that we'll talk about in the next couple of slides. Cool. Thanks everyone for responding. I'm gonna carry on and close this poll. Okay. Where are we? Okay. So moving on to the next challenge. Sorry, there's one more challenge. And this is a big one. This is one that we see again and again when we talk to fraud teams. Their models are achieving amazing accuracy, in the high 90th percentile when they're in testing. but then they drop down to around 50-60% accuracy in production. And why this happens, this is an important problem to solve because it represents a pretty massive opportunity for fraudsters. And when your models aren't performing, as expected in production, you're leaving the door open for attacks. And the root cause of this, why this happens, is often the subtle inconsistencies between how features are calculated in training versus how they are served. Your data scientists might work in, with one implementation of a feature when training models, but then the production environment uses a slightly different calculation. So these subtle differences compound and lead to significant performance degradation, or they can. And this is, training serving skews, what it's called. It's particularly problematic for fraud detection, where small signals can mean the difference between, correctly identifying an attack or, maybe mistakenly locking out a legitimate user, which you don't want to happen. So now we've talked about 4 technical challenges, and now we're going to talk about how these drive the kind of 4 requirements that we see for effective ATO prevention. The first one being rapid iteration and experimentation. So we've talked about how attack patterns evolve consistently all the time, and your team needs to be able to quickly iterate on new features without going through a lengthy engineering cycle to do so. So if it takes weeks or months to implement a new fraud signal, you've already lost too much time. Data scientists, they need to be able to define and test new features, and engineering teams need to be able to get those into production quickly. You also need to complete data integration across multiple timeframes, so that having your historical data and real-time and streaming data, being able to incorporate fresh signals from streaming and real-time sources alongside your historical patterns, so you can compare to baselines and normal behavior in the moment. That means handling, batch processing, stream processing, and real-time computation within a consistent framework. And that's something that batch-centric data infrastructure just wasn't really designed to do. The third requirement is low latency delivery. So when a user attempts to log in, you have, maybe 200, 300 milliseconds to evaluate hundreds of signals and for that model to make a decision. And this requires specialized infrastructure, again, that can deliver feature values with extremely low latency while handling, potentially large traffic volumes. And then lastly, you need that training serving consistency in order to achieve and maintain the accuracy that your models need. So your features need to be calculated identically across both training and serving environments, and make sure your models can perform as you expect them to in production. So last poll here. We're gonna, before we move on to Tecton's approach, I really want to understand what types of fraud signals you're currently evaluating or working with. So that will be what our next poll question is around. Let me go ahead and open that now. You all have been great with the polls so far. Thank you. Okay, so this question is, which types of fraud signals are you using or evaluating? There's IP reputation. These are kind of all typical signals that we see in ATO use cases. Device fingerprinting, behavioral anomaly detection, transaction history, geolocation, login velocity or patterns, network connection, attributes, and then social graph analysis, or we don't use signals yet, which I don't see any votes there so far, but. Oh, wow, okay, IP reputation is top so far, and then coming in second is behavioral anomaly detection. This is awesome, got a lot of votes on this one. Great. Thank you all for responding. This is really interesting. Looks like the most common ones are IP reputation, behavioral anomaly detection, transaction history, geolocation, login velocity, and patterns. Those are super common, I see. Cool. Okay, I'm going to close this one out, and then we'll talk about Tecton's approach real quick before I hand it off to Sergio. Okay, so where does Tecton fit? Tecton operates as the central feature engineering layer in your ML infrastructure. So we bridge the gap between your raw data sources and your fraud detection models. So on the left side, you can see we connect to all of your data sources, your real-time APIs and SDKs, streaming platforms like Kafka and Kinesis, your batch systems, so your Snowflake, BigQuery, whatever data warehouse you use, and then even your unstructured data sources. So if you're using unstructured data in your fraud detection models, we'll connect to that as well. And then we integrate with your preferred approach to model deployment. So whether that's flexible online inference through like a framework like SageMaker, or custom serving solutions, offline training through your existing systems there. So Tecton isn't replacing your existing data infrastructure or your model serving platform. We're actually providing the critical middle layer where the infrastructure that transforms your raw data into ML-ready features and serves them at low latency to models. So we'll take a look at what that looks like under the hood. Sorry, I lost my place. Where are we? So the Tecton platform, we connect to your data sources, like I said. And sorry, hold on, let me find my place. My screen is not responding. This is the problem with live presentations. Looks like my computer might be frozen.
Want to jump ahead and let me share the screen and do the demo, and maybe we'll come back to this. All right,
Yeah,
let's do it.
That works. Thanks, Sergio.
All right. So if you can stop, there you go. You stop your screen share. I'll start mine. Hold on. Entire screen. And there we go. Okay, so let me set the stage. So like Julia mentioned, we are, in this demo in particular, we're in SageMaker. We're using the Jupyter Lab environment in SageMaker. And obviously this had to happen just as I started the demo. So you'll have to bear with me here. Oh, the demo gods are not being nice to us. Hold on a sec. I will restart this in no time. If I leave it idle for a little while, I lose my session. So let me get back in there. Jupyter Lab. Oh, it actually stopped running. I guess I left I left my instance idle a little bit too long.
You're going to take it back over if you'd like. My screen.
Yes. Okay. Let me do that.
Okay.
Sorry, folks. Technical difficulties.
You know, this is the danger of doing a live show here. Share screen. Okay, great. Okay. So we're back to showing how Tecton works under the hood. So like I said, we ingest data from your batch streaming or real-time sources, and we transform it into any type of feature that you need using your business logic. So we load those features into both an offline and an online store. There we go, let me catch up. Online store, and then we serve those features for both model training and inference. But what makes this powerful is that we are unifying some fundamentally different pipelines that we talked about before. So batch streaming, real time, on demand. And we provide a declarative framework that gives you the same experience working with those different data pipelines. So you're defining a feature the same way, whether you're defining it from a batch source, a streaming source, or a real-time source. And that enables you to get the freshest signals to your models without having to build and maintain separate infrastructures for each data type that you work with. So think about what this means for your teams. It means your data scientists can work with a unified API that abstracts away the complexity of the underlying infrastructure. They get to just define features one time, and Tecton automatically handles the appropriate processing based on the data source. So how do we do this? How does this work? This is an even deeper view of the declarative framework. So first, you start with a simple Python feature definition. You can write Python. You can write feature definitions in Python. You can use SQL, Spark. But either way, it's a simple definition that describes your business logic. And this definition is declarative. So you specify what you want to calculate. For example, you might want to define a feature that counts login failures over the past 24 hours for a specific user. And then Tecton ensures that the implementation is consistent between training and serving environments. The same feature definition is used to generate both training data sets and real-time feature values. So it eliminates that training serving skew that we talked about earlier. And then finally, the platform automates serving, the scaling, monitoring, all that good stuff. Once your features are defined, it'll handle all of the infrastructure required to make those features available to models. And then kind of the net of all of this is that it speeds up the development cycle for new fraud features, because this collaboration between data scientists and engineers, it's a lot more seamless. Data scientists don't need to throw their feature definitions over the fence, so to speak, to a data engineering team in order to implement them in production. And we find a lot of teams are able to get features into production a lot faster, in a matter of days rather than months when they're using Tecton. And we talked about why for account takeover, low latency is critical in particular. Tecton's architecture is specifically designed to deliver millisecond level feature serving. And at the core of this is our feature retrieval system. So this is what it looks like. It includes an online store which pre-computes feature values. This store is optimized for low latency reads, ensuring that common feature values can be retrieved almost instantly. And then we have advanced feature caching capabilities to enhance performance for frequently accessed features. So this further reduces latency. We've got feature servers that assemble the complete feature vector from multiple sources, which handles the complex logic involved combining pre-computed features with real-time calculations. And then the transform servers handle on-demand feature calculations for values that need to be computed at request time. So that could be, like the distance between a user's current location and their typical login location, for example. And all components are independently scalable. So this allows you to maintain performance even during those, potential traffic spikes. And all in all, this architecture enables you to retrieve feature vectors with hundreds of signals in just a few milliseconds, even at scale, which is what you ultimately want for account takeover. So if you remember, oops, skipped a slide. If you remember that accuracy gap that we talked about earlier, this is how Tecton solves it. We solve it with a single feature definition approach, which I talked about a little bit with the declarative framework, but a lot of teams end up building actually separate implementations of training and serving, which leads to inconsistencies. So like we talked about, data scientists might write feature definitions using SQL or something like that for a calculation, and they use that during training, while they throw it across the fence, and then engineers implement a separate version of that feature in a language like Java or Python to go into production, right? Well, Tecton uses a single definition, and it allows you to use a single definition for both training and serving. So your features have identical distributions in both training and serving environments, which makes your models perform in production as you expect them to, or as they did during testing. Basically, no more like mysterious performance drops when your model goes into production, is what this means. So to summarize all of that, ATO is usually one of the first use cases that our customers implement with us, because we help to shorten the production time to production with our declarative framework. Just to repeat what I said, like you define features once in a familiar language. So it could be Python, SQL, Spark. Tecton handles the rest. We ensure that online-offline consistency, which eliminates train-serve skew and makes your models more accurate. We enable seamless CI/CD integration with your existing DevOps workflows. So that means your features can be versioned, tested, deployed using the same processes that you do for other code. Low latency transformation for streaming and real-time features, so you can incorporate the freshest signals into your model's decisions. And then lastly, we provide high scale, low latency online serving. So your features are delivered in milliseconds at scale. Without Tecton, teams usually have to build and manage all of the infrastructure that you need in order to do this. But you don't have to. We've solved all of the hardest stuff for you and battle tested it with some of the largest fintech and finserv companies out there. So with that, I will hand it off to Sergio to show you how it works.
All right, let's see what the demo gods have in store for me. Looks like everything's
I think
ready.
we got out with my slides.
It's all good. All right, so back to, I was saying, we're in Jupyter Lab environment that gives us this kind of IDE with a notebook environment. You don't necessarily have to use SageMaker or Jupyter Lab for that matter. Any model training environment or model serving environment that you use is something that you can integrate with Tecton. But anyway, let me talk about the demo. So in this demo, we're doing an end-to-end demo of an ATO detection system, right? And the way we've deployed it here is our front end is going to be the notebook. I'll show you a little form where we simulate the login requests. It talks to an API gateway set up on AWS, which talks to a Lambda function. This Lambda just has the application logic or the detection logic that talks to Tecton, retrieves a feature vector from its feature serving layer, use that feature vector to then get an inference from the SageMaker endpoint, maybe processes that result with some logic, and ultimately grants access, requests a two-factor authentication, or denies access for that login request. So let me switch over to, turn this off, and switch over to the Tecton UI. So in this initial environment, we've already deployed a series of pipelines, and I'll show you how they're built in a second. But just to give you the landscape, we have login history, so login attempt history with failures and successes. And we use batch feature view to establish a baseline of the user behavior. So we calculate some features about how many times they normally failed before they succeed, that kind of thing, the ratios, the last successful timestamp, login timestamp, and so forth. We have another batch feature view that calculates the user's device fingerprints and the ones that are normal for that user, so that we can compare later in real time. And we also calculate the recent activity through a streaming pipeline. Where we're calculating similar features, the number of attempts, number of failed attempts, and last successful time intraday. All of these pipelines feed within Tecton. Tecton takes it automatically manages the online store and maintains all the latest features in the online store and keeps the history of all of those feature calculations so that you can use for training. We also have an example of a real-time feature view. This is where at request time we're getting some inputs, and we're also using some of the pre-calculated features to calculate final features before serving them through a feature service. So this is what a Tecton pipeline looks like and what it looks like for this demo. Let me go ahead and show you it running against those pipelines. So let me start my form here. And so this is that login simulation where we have the login data, the inputs that usually come in a login request, things like the user ID, the IP address, and the browser and OS information and the type of device. So when we submit that, we're following that whole path that we described, right? We're going into the Lambda function that is requesting the feature vector from Tecton and retrieving those features and calling SageMaker, getting a prediction, and finally processing that logic to deny access. Just to show you here that this is actually live and we're retrieving other users. I have another user ID here to test. And here we go. We retrieved a different feature vector. This guy clearly doesn't have much activity. In the other one, I actually ingested some recent events into the stream, so that way it has recent activity. But this one, because there's no recent activity, has a low risk and access is granted. The other thing I show you, let me run a few of them. You see the elapsed time, 34 milliseconds, 32 milliseconds. So this is really low latency, and it's doing all of it, right? It's retrieving the fresh features and doing the inference. And so I'm not going to talk through this again, but this is what Julia described, that how we deliver that, right, with all the scalable infrastructure and the feature retrieval system that Tecton manages automatically. So now I'm going to show you what the experience is like for the data scientist, right, for feature engineering in general. Like Julia mentioned, we start with a declarative framework, a simple definition that you deploy Tecton, and Tecton takes care of all of the rest, managing the infrastructure, managing the online, offline stores, and the serving layer. In ATO, streaming is important, like Julia mentioned, and we need to understand the recent activity, and this is typically one of the harder parts to get right, to build the streaming infrastructure that calculates features. In Tecton, we make it really easy. Just define a streaming source where you define where the stream comes from. In this case, we're using a push config. That means that you can push events directly into Tecton. You could also configure Kafka or Kinesis here, and a batch config that holds the sync of the stream, right? This is where the streaming events history is stored. The reason we use both in streaming pipelines is that we're going to apply the same logic. Oh, before I go on, this is what that data looks like, right? We have, events, login attempt events, the browser information, whether the login was successful or not. You declare features for entities. Here we're declaring features for a particular user, and they're identified by user ID. On the feature view itself, the streaming transformation is really easy to define. You select what you want, the mode of calculation. Those are all the compute modes that Julia mentioned. In this case, we're building time window aggregations, and each aggregation is really simple to define. You just list an aggregate within the features array, give it a name, select an aggregation function, a source column, and the time window. And we support a very wide variety of time windows. These are just, last minute, last 10 minutes, last 24 hours. But you could also do, delayed time windows, hopping windows, sliding windows, and even time series with the time window definition. And Tecton takes care of all of the logic to build those different time windows and do so efficiently. You also specify your materialization requirements. You want it to feed the online store. You want it to feed the offline store. And how far back in history do you want it to build in the offline store for training? How often you want it to run that offline update? And finally, it's Python. Well, depending on the mode that you selected, it can be Python, it can be SQL, but in this case, it's a Pandas. So you get a Pandas data frame, you process it with Pandas transformations, and return the result into the aggregation engine that then takes those transformed inputs and does the aggregations that you asked it for. Within the notebooks, you can test your feature definitions as you're defining them. So this will go and access the source data and do the calculations that you requested and give you an example of them, so that you can check your feature engineering. Whenever we use aggregates in a feature definition, that engages Tecton's aggregation engine. This is a specialized engine for low latency, low cost processing of all sorts of time window aggregates. And the way it works is it takes the event data, whether in batch or stream. It uses a partial aggregation approach that reduces the amount of storage needed online. And then because there's less rows, less partial, instead of all the events, less partial aggregations, we can do at read time, pick the right partial aggregates that we need for a particular time window and build those fresh feature values with very low latency at a low cost. Batch feature development is also important in ATO because you need to establish the baseline of login activity or user activity. So this is an example of that. I'm not going to go into details. Again, it's a source, and now it's a batch source, and the feature definition is just like the streaming feature definition. So this is where the declarative framework really helps in this process, because we're defining feature streaming pipelines and batch pipelines with exactly the same kind of code. All right, the same declarative framework, and the only difference you see here is the windows are bigger, right? These are days instead of minutes, and same materialization approach. Tecton takes care of all provisioning the infrastructure that's needed and scheduling the jobs, and at the time a job needs to run, provisioning the resources, executing and monitoring the jobs. All you need to do is define this function. Right? You define what features you want, how to transform your raw data, and the rest of the process is managed by Tecton. And again, you can test those features. And then we come to real-time. Real-time features are particularly important in low latency use cases like what we're talking about here. So at the time you're solving a problem at the time that of the request, a login is occurring, you need to solve it before the login is successful or it fails. And sometimes you need to calculate features in real time that take into account the input features that come in the request and pre-calculated features that have been calculated from streams or batches to get the fresh values for all of them, and maybe do comparisons to calculate things like an amount acceleration or whether a user device fingerprint is a new one or not. And that's exactly what this one does. The definition here is, again, very simple. A source, a request source just defines the input parameters that you expect to receive at request time. The real-time feature view can incorporate any number of other feature views. So it incorporates that request, which is the request data. It incorporates data from the baseline behavior, from the streaming behavior, and the user's device fingerprints. And now we're using, instead of aggregates, we're using attributes. And this just means that we're going to calculate this set of attributes as the output to the function based on these inputs. And we define a function in Python or Pandas. This is a Pandas example where all of these come into the function as Pandas data frames, and you just process them with Pandas. Here we're calculating the fingerprint, determining if it's a new device, calculating failure rates over 30 days and over the last 10 minutes, and returning those. So that's how you define both streaming, batch, and real-time pipelines, and it's all with that same declarative ease that Tecton provides. You can test real-time pipelines with mock data, by simulating the data of those data frames, and just test it here locally to test your logic. And the end of the pipeline, like we said, is the feature service, right? This is just really think of it as a view, a declaration that gives it a name and selects from either from multiple feature views. In this case, from the baseline, we're selecting some features. From the streaming, we're selecting some features, and we're getting all of those real-time features included in the feature vectors that we want, both for training and serving. There's a test of generating some training data with all of those features included. And I'll talk a little bit more about generating training data when I talk about training. So what's next? You develop these features, and I don't know if you noticed, but the way I'm working on in this notebook is I'm writing this code out to this file structure. Essentially, you're creating a Python package, right, with the set of object definitions that make up the declarative framework, the features as code. And when you're done, most of our customers have some kind of CI/CD pipeline integration. This is an example with GitHub Actions, where you integrated the process into your normal DevOps or MLOps process, where you have a versioning of the code in a GitHub repository, and you have GitHub Actions. So as new features are deployed, they're peer reviewed, and once they're merged, they're applied to the platform. So most of our customers integrate it that way. This is a demo, so I just went ahead and did an apply, and the apply analyzes your code, makes sure there's internal consistency, that the data types match, that the data sources that you need for your transformations are all there, and it creates a plan of execution on the platform. And that's what I ran before today to build out these pipelines that I showed you, and that's what's driving that demo. Now, once you have pipelines deployed, you want to train a model. And that's another point where Tecton helps, right? So as with every model training exercise, you start by reading some event data, right? Some labeled events. We're just doing a little bit of transformation on it and this particular data set. But a training set of events have to have certain characteristics. They have to have time, because we're going to produce training features, we need to go back in time and see what the feature values were at that point in time. And that's what this process is going to do. You'll need to identify the business entities, in this case, the user for which I'm getting features, and any of the other inputs that you need for those real-time calculations. Remember that the real-time request required some of these. And finally, I don't want to do that. Finally, the label, right? Whether this is an ATO case or not. What Tecton does to retrieve the training data is it takes those events, that set of events that you defined, and it does the time-aligned joins using the entity IDs and the timestamps with the data that's stored, the historic data that's stored for the features in the offline store, to create time-traveled features. With those time-travel values, it applies them to the real-time request or the request time feature calculations with any of the other inputs that it needs from the events, and puts all of those together into a training data set. Now, this is all under the covers what Tecton is doing for you. All you really need to do is access the workspace where the feature service is deployed, request the feature service that you're interested in, the one where we just defined the features for, and get a data frame, training data frame, which can be a Spark data frame or a Pandas data frame, by calling get features for events with the set of events that you just defined. And that's it. You get the training data. The rest of this notebook is really not about Tecton. It's really the training of a model using SageMaker. So I'm not going to go into any of that detail. But anyway, there's a rebalancing of the classes. There's the execution of a training job in SageMaker, the deployment of that model, the evaluation of performance, and let me just show you the performance results, which I thought were really good. Now I don't really believe it. I think this is an overfitting. I think my resampling strategy may be wrong, but that's not the point, right? The model that this isn't an example of a really good account detection model, but it's really an example of how you do feature engineering and how fast it is to do with Tecton. So in that spirit, and let me check time. I have a little bit more time. Part of the process of building models is the iterative nature, and the fact that attacks are varying, the attack vectors are varying, means you have to adjust your models. You have to add more features and train other models and continuously have that cycle. So I'm just going to walk you through an example of integrating an IP Insights model into these pipelines. So IP Insights is an AWS SageMaker model type that distinguishes between normal user IP behavior and irregular IP. So random IPs here for those users you see provide a different score, a higher score, and we use that score as input. And in order to do that, I'm going to actually go ahead and modify the pipelines just to show you how easy it is. So in this case, I'm using an external API to calculate a new feature. So in Tecton, you define a resource provider, which the resource provider in Tecton manages secrets. So if you need an API key to access an external service, you can access it here through the context. Because I'm running in AWS within my VPC, I don't need a key in this case. So I just click create a function that returns a predictor for a SageMaker endpoint where I deploy that trained IP Insights model. And then I can integrate it into a real-time pipeline in Tecton. I actually have to go run these so I get that new code. What I'm doing is I'm writing that code out to these feature folders so that I can apply them. But let me walk you through the real-time one. You just specify the resource provider, again, specify what you're going to, the features that you're going to output, what input you need at request time, and essentially do the calculation, right? Get the model inputs, run the predictor in real time. So this is an external service call to that other endpoint, get the prediction, and do some logic here to calculate the score and the whether it exceeds a predefined threshold or not. So in real time, we're ready to calculate that and to access that external API. We can also do this in batch, and you actually, for training, you actually want to do it in batch, because if you were to generate training, let's say you have 1 million training events, you don't want that to be individual calls for each of those events to the endpoint, because it's going to cause a lot. So you want to do it in batch instead. So we define a batch feature view that does just that, right? It uses the same resource provider, but it batches up the execution of those predictions and uses the predictor to do batch executions, 100,000 rows at a time, right? Or whatever your API allows. And it's that simple. Let me see, you could test them again. I'm running out of time here, so I'm accelerating. You can also isolate. Well, when you're using external APIs, you have to isolate that workload into a separate transformed server group running in the serving layer. So this is how you define it. It's really simple. Give it a name, define a scaling configuration with the minimum and maximum nodes, and what environment it needs. This contains all the packages that you need for the execution, including the SageMaker package. So let me define that. And finally, the feature services. We declare one for inference, one of the feature services, which uses the new real-time pipeline, and declare one for training, which uses the batch pipeline, so that we don't incur those additional costs. So I'm going to define those, and then I'm going to show you what it looks like to deploy them to Tecton. So let me go to the right directory here and do logging to Tecton. So I'm logging in to the Tecton platform so that I can interact with it and apply these new features to it. Logging to the community cluster, get my authentication token. So this is integrated in our case with Okta, and your case, it can be integrated with whatever your authentication system is. So that's why I didn't have to type in a user ID. I just need an authentication token. And finally, I do a Tecton apply that does the analysis of what's already there and what I've added, and it finds that my new the new batch and real-time feature views for IP insights need to be deployed, the resource, and the new services. So I go ahead and say yes to that, and it's applied. So let's take a look at what that apply did. So if I go back here and refresh this screen, you'll see the new pipelines have been added. There's the batch pipeline for IP Insights that's feeding the offline store and that drives the feature service for training. And you see the real-time pipeline that we've added that drives the service for inference, for the feature service for inference. So it's that fast. In the UI, you could also see, explore, and one of the things that Tecton drives is the reduction of pipelines, because people are, teams are usually siloed at many companies where you get data pipelines that calculate the same things multiple times. So that also reduces the cost. And by having everything in one central place, let me see, it's the search here. You can search for whatever's already been created, right? So that you're not feature engineering things that have already been done. So if I look for user, I see all of the feature views and entities that we have for user. If I look for merchant, we have some for merchant, and so forth. You could just do a global search to understand what's already deployed on the system and what you can reuse. You can look at the jobs and the materialization, how that's going. All of these just completed, and monitor the environment in general. So with that, I know we have very little time left. I'm going to stop sharing and let Julia finish us off and see if you guys have any questions. Let me find the right screen.
Okay. While Sergio does that, I am going to reshare my screen, and we'll wrap up here by talking through a quick case study. I think this is really kind of just illustrates and summarizes everything that we just talked about. This is a leading cryptocurrency exchange that's using Tecton to help them secure millions of dollars worth of crypto assets. And because they're a very popular crypto exchange, they are a prime target for pretty sophisticated attacks on a daily basis. And before buying Tecton, they had three major challenges. First was scale. They needed to manage thousands of features across hundreds of pipelines with consistent performance. A second one was agility. They were struggling with the ad hoc feature engineering bottlenecks, as Sergio mentioned, like how that can happen. And when new attack patterns emerged, it took them weeks or months to implement their countermeasures, which was just not fast enough for them. The third was speed. So they needed millisecond level detection for billions in transaction volume. So their existing infrastructure couldn't deliver that. It couldn't deliver the low latency that was required for their fraud prevention to actually be effective. So these challenges are, pretty representative of what we see across the industry. Complex infrastructure requirements combined with the need for rapid iteration and response to constantly evolving threats. So Tecton helped solve these core challenges. They needed sub-second detection and response to prevent account compromises before damage occurred, and Tecton enabled them to do that by incorporating fresh data, fresh streaming data into their risk signals for their models. So their models can now take into account up to the second data and make more informed, context-aware, real-time decisions. Tecton also helped with the low latency requirements. So with ultra low latency feature retrieval, they can now make complex risk assessments without impacting their user experience. And then lastly, Tecton alleviated all of the heavy lifting of building, maintaining, optimizing infrastructure so that the data engineers on their team and the data scientists can focus on developing better models and not all of the data plumbing underneath. So quickly, just some of the outcomes from the business side. They're able to protect their user accounts from unauthorized access and dramatically reduce the infrastructure overhead. And this enables, their single engineers to own the entire feature pipelines, own entire feature pipelines instead of requiring coordination across multiple teams. And that accelerates their time to market significantly. For developers, they achieved self-service feature development. So without the engineering handoffs, and gained the ability to rapidly iterate. Oh, did we end? Okay. Might have gotten cut off there. Not sure. I think this quote captures the essence of what Tecton does, which is remove the bottlenecks that prevent organizations from fully leveraging machine learning for critical use cases like ATO prevention. And with that, I just want to thank you for joining us. If you're facing any similar challenges to what we talked about today, we'd love to hear from you and figure out how we might help your team. If you're wanting to try Tecton for yourself first, you can check out our interactive demo at the URL there. And thank you again. Have a great day.
Thank you.